So, are each of the series below geometric? If so, determine if the series converges or diverges, and if it converges, find the infinite sum. So, we have a couple formulas for the infinite sum if we need them, depending on whether we start in the first term or the zeroth term. Either way, it's the same idea. It would be the first term that you'd list, whether you plug in a 1 to get it started or a 0 to get it started. So we will just crank out a list. Now, we won't always need to crank out a list in order to do this, but I'm going to for the first 1 or 2 or 3. So 0 goes in here. If I plug a 0 in here, I'd have 3 times 2 to the 0, that's 3, plus, okay, plug in a 1, I'd have 3 times 2 to the 1, that would be 6. Plug in a 2, that would be 3 times 2 squared, which would be 3 times 4, which would be 12. And we'll keep going from there. And we will add all those up if we can. So first of all, let's talk about whether or not it is geometric. Is this a geometric series? Am I moving from one term to the next by always multiplying by the same thing? And the answer to that is yes, I am. It is geometric. So let's switch colors here and let's start writing answers in red. Yes, it is geometric. And then the question is, does it converge or diverge? Well, let's see. 3, 6, 12, 24. It's going to get bigger and bigger and bigger. So this one's going to diverge, and therefore we don't have to do anything else. These formulas are null and void because it's getting bigger. Okay, let's approach this from a different perspective. Let's suppose we don't want to make this list and we want to clear our throat. So what we should do is look at the structure of this and compare it to the explicit form of a geometric series, and we can see that they really are the same thing. So your zeroth term, the first term technically, but you'd plug in a 0 to get it, would be 3. And then r is your common ratio, and then you're raising it to the n power. So everything is perfectly aligned right here. Sometimes you'll have to manipulate this a little bit to make it look like one of these, generally this one. But in this case, everything is exactly the way you need it to be. So you could say, well, r equals 2, and that's good to know because r is equal to 2, then r is greater than 1, and therefore this thing is going to diverge. So we really didn't have to make the list to do it. We could have just looked at the structure and figured it out that way. All right, let's slide up a little bit. I feel like this thing keeps shaking, so I'm going to slide that up. And here we go. Is this, oh, and there we go, it's moving again. Is this the same structure as either one of these? And the answer is yes. So these two are the same general structure. And in that case, r would be 1/2. And so let's write that down. R is 1/2. You can make a list if you want to. You can check it twice. Going to find out who's geometric or not. Plug in a 0, you'd get a 3. Plug in a 1, you get 3 times a half. That'd be 3 halves. And then you'd plug in a 2 and you'd get 1/4. So 3 times 1/4 would be 3/4. And these numbers are getting smaller. And you're basically multiplying by 1/2 every time. So didn't have to make the list, but we did. So yes, it's geometric. And it is geometric, therefore I can decide if it converges or diverges. And so because r is 1/2, r is less than 1. Let's point here instead. There we go. R is less than 1. Now, I'm reluctant to say, oh, r is less than 1. That's great. What about -5? What if r was -5? That's less than 1. Well, that would be outside the other end of the boundary. R is actually between -1 and 1, which goes back to this conversation. We had one-sided conversation in the video, I guess, about the absolute value of r being greater than or equal to 1 causes it to diverge. And so the opposite would be true when it is between -1 and +1, non-inclusive, so open interval, then it will converge. So this one's going to converge. And we're going to find out what it converges to. So let's switch colors again just for fun. Let's go purple. And we're going to use this formula. What do you want to use that one, not that one? It doesn't matter. So what's the first term? 3. So 3 over 1 minus 1/2. There's a reason this formula works. Do you want to know why? Too bad, I'm not going to tell you. We're going to do this one in our head. 3 over 1/2 is going to give me 6. If you added 3 plus 3/2 plus 3/4 plus 3/8 plus 3/16 plus 3 over 32 plus 3 over 64, and you keep doing that, you're going to eventually get a number that is so close to 6 you can smell it. Okay, I did just say I'm not going to tell you where this formula comes from. I do want to tell you later, though. Let's move on to the next problem. At the end of this video, it's going to be this optional hang around if you want to see the rest of it sort of thing. Is this structured like a geometric formula? And the answer is yes. Now, my paper is not front and back. Mine is just one-sided, but if you flip it over, you'll see that. This is the same as that, so we can identify the parts. A sub 1, the first term, we are starting with n equals 1. A sub 1 is, in this case, 1. So there's an understood 1 there. And in this case also, r is equal to 0.6. So if you wanted to, you could write, oh, r equals 0.6. R equals 0.6. Because 0.6 is between -1 and 1, then this thing is going to converge. So let's do it. This is a geometric, I'm just going to abbreviate geo, and I'm going to say that it converges. And so therefore, we will find what it converges to, using the purple pen, of course. So our first term is not 0.6. Our first term would be what we get if we plug in a 1. Plug in a 1, you get a 0 for the exponent. 1 times 0.6 to the 0 would be 1 over 0 minus 0.6. And that's going to give me 1 over 0.4. And we're going to do some stuff in our head. Let's see. 0.4 is 4/10. That's 5 halves. I'm just going way too crazy here, writing way too much that happens in your head. So let's see. No, 2/5. Sorry, I was thinking ahead. That's 2/5. We would reciprocate it. It would be 5 halves. So 2.5. 2.5 would be what we get. All righty. The next one. We grab our formulas. We look. We're like, oh, is this geometric or not? It's kind of hard to tell. Does it look like either one of those? I don't know. So maybe this is one of those that we have to beat up until we can decide if it is or not. So we actually have a couple options. We could generate the list. Let's do that first. Sounds exciting. Let's do it. Let's plug in a 1. If I plugged in a 1, I would have 2 over e to the 1/2 plus, and then I'm going to plug in a 2, and I'll have 2 over e to the 2/2, and I'm going to leave it as 2/2 because I want to sniff out a pattern. And then 2 over e to the 3, e, not 3, silly. E to the 3/2, and then you can see where this is going. So I wonder if this is geometric or not, and still kind of hard to tell. So what you could do is, and this is an extreme way of doing it because, I'll go ahead and tell you, this is geometric, and there are other ways to get about it, but I'm going to go a little crazy on this, and I'm going to try something that I could have tried, like if I was completely number ignorant, I could have tried it here. If I looked at that list and I said, man, I don't know if it's geometric or not, try it. 6 divided by 3 is 2. Now, please, you're in calculus. Don't type 6 divided by 3, but I'm showing you a process. And, 12 divided by 6 is 2. Oh, yeah, I'm multiplying by 2 every time. Because if I divided, I'd be, figuring out what I'm multiplying by. So we can actually try that here. And we could do, no, let's go real crazy on it. Grab a scrap piece of paper here. Grab me some scrap paper, and let's try it this way. What I want to do is divide it. I'm going to do second term divided by first term. 2 over e to the 2/2 divided by 2 over e to the 1/2, which gives me 2 over e to the 2/2. I'm going to keep it like that because I want to, times e to the 1/2 over 2. Cancel those. And then I have e to the 1/2 over e to the 2/2. And then if I subtract my exponents, I'd have e to the -1/2. Right? Okay, so what did that tell me? That told me that if I multiply by e to the -1/2, I'd go here. So we actually just did that same thing on the most elementary level when we were like, oh, 6 divided by 3 gave me 2. 12 divided by 6 gave me 2. So maybe, just maybe, if we try it again, going from here to here, we'll get the same thing and it would work. So here we go. 2 over e to the 3/2 divided by 2 over e to the 2/2. That is equal to, not times, that is equal to 2 over e to the 3/2 times e to the 2/2 over 2, cancel, cancel. I'm left with e to the 2/2 over e to the 3/2, which is e to the -1/2. Oh, it works. This one is geometric. So yes, geometric. I'm going to do it one more way though. I want to show you one more way to sort of beat this up and beat it into submission. Okay, you're gonna see it when it happens. You're gonna say, man, that's amazing. But before I do, let's just go ahead and jump over here and we're gonna say this is geometric. Does it converge or diverge? Well, don't know. Let's play that game in a minute. Let's start beating this thing into submission to make it look the way it needs to really look. And I am gonna make it look the way it needs to look by forcing it to be like one of these. Okay, now which one do you want it to be like? Really, it doesn't matter. You could say, oh, it starts at 1. Let's start it here. I don't care. I really don't care. Now, technically, you could be like, oh, because it starts at 1, well, you go for this one. Who cares? But here's the deal. The exponent is an n. Let's let the exponent be an n, and only an n. Is that the only way to think about it? No. But is that what we're going to do? Yes. So I'm going to take this, and I'm going to bring it down here. I'm going to say this also equals this down here. So this is the sum from 1 to infinity of 2 over e to the 1/2 to the n. Okay, so totally doable because, I know that's really blurry. There we go. This is e to the 1/2 to the n because 1/2 times n would give me n over 2, which is what that is. And a power to a power, multiply, right? So now we have a situation where we have the sum from 1 to infinity of 2 e to the negative 1/2 to the n. That's what we have, okay? Does this look like that? You bet it does. And there's that e to the negative 1/2 again. So my common ratio is indeed e to the negative 1/2. And so truly is geometric. I found a common ratio. Now, again, I know I'm starting at 1, and it doesn't quite look like the structure where you start at 1, but the general structure is there. So it's not a huge deal that it doesn't look a certain way. Now, question is, does it converge or diverge? Well, what's e to the negative 1/2? Let's keep beating this up. I have 1 over the square root of e. All right. What is the square root of e? Okay, well, e is 2.7-ish. The square root of 2.7 is, well, less than 2.7. It's between 0 and 2.7. Okay, so I'm pretending like this is calculator inactive for a second. So the square root of e is the square root of about 2.7, which is going to be less than 1. Now, if you want to get technical, because it's not negative, we could say that this is between 1 and negative 1, and for that reason, this thing's going to converge. Converge to what? Now, I want to pause here and warn you. As we move forward in these lessons, not in this lesson, but as we move forward in these lessons, you're going to say, converge to what? You won't always know. With geometric, you will. With geometric, you have some lovely formulas. With a lot of the other ones, you won't. What if it's not geometric? You don't know sometimes. Sometimes the best thing you can do is estimate. We don't know what these things always converge to. Sad, but true. So let's find the sum using the sum formula that I usually write every time I write it, every time I do it, but I didn't write it this time. So we're going to use that formula or that one. Let's go with this one because we'd start with plugging in a 1, or doesn't generally matter. But if I plugged in a 1, my first term would be 2 over e to the 1/2. It actually does generally matter. We need to be careful with that. Be careful with what I say here. 2 over e to the 1/2. That's my first term, and I plug in a 1. And it works here. If I plugged in a 1, I'd have 2 e to the negative 1/2, which is this. And then 1 minus my common ratio, which is 1 over e to the 1/2. You could call it this. You could call it that. Either way you want to call it, as long as you call it. And we're going to beat this up. When you have a complex fraction like this, I have a great recommendation. Why don't you multiply everything by e to the 1/2? It's going to wipe out the denominators within your denominators. Oops. I put those parentheses in the wrong place. Oh no. E to the 1/2, and you multiply this guy by e to the 1/2. There we go. And we're going to cancel those and cancel those, and we're going to be left with 2 over e to the 1/2 minus 1. And that gives me 2 over the square root of e minus 1. That's as far as I'm going to go with it. Like, don't go any further with that. And we can get all complicated with things, but let's not. Let me double check it. I'm going to make sure I'm right. Yep. Okay. Let me go calculator on this thing. I want to double check, because if I'm wrong, I might cry myself to sleep tonight. 2e to the negative 1/2. That's my, whoa. That's my numerator. Divided by 1 minus e to the negative 1/2. and I get this, which should be equal to this. If I made a mistake, I'm gonna have to back up and fix it. Yeah, same thing, fantastic, good to go. All right, let's move on to the next one. And the next one is not listed with summation notation. A couple of them aren't actually. So let's figure out what the pattern is. And if we can sniff out the pattern, maybe it's geometric and we'll go from there. How do you turn a 1 into a 0.4? Now you could subtract 0.6, yeah. But if you subtracted 0.6, it wouldn't move you forward in this pattern, okay? So you could multiply by 0.4. Well, what's 0.4 times 0.4? It's 0.16. If what's 0.4 times 0.16 is 0.064. So yeah, we are multiplying by the same thing every time, and that thing is this. And when in doubt, divide it out, for real. Second term divided by first term will give you that. Third term divided by second term will give you the same thing. The pattern continues as you go. So this one is also geometric. And because this number this is the common ratio, is between -1 and 1, this thing's going to converge. So we have a series that converges, if I could spell, converges. And let's keep driving this train. First term is 1. 1 minus 0.4. And it's going to look a lot like this one up here, but it's just going to be a little bit not like that one up there. Let's see, 0.4 would be 0.6. And that is 1 over 3/5, which is 5/3. All right, 3 more, and they're going to go kind of fast, and here's why. Here is why. Everything's been geometric up to this point. You can kind of guess where this one's going. No matter how hard you try, you will never, ever, ever be able to make this look like either one of these. And here's why. There are subtleties to it, but this one's a little more of an obvious subtlety, so I guess that's an oxymoron. Notice the n is in the exponent. The n is in the exponent. That n is not in the exponent. So this one is not geometric. So for each of the series, is it geometric? No. So it's not geometric. So I'm not even going to talk about if it converges or diverges. I'm not going to find out what it converges to if it converges. I'm not going to play that game. There will be tools later where we will look at that structure and decide if it converges or diverges. It converges. And we might even be able to figure out what this converges to. We're not. But if you do want to know what this converges to, it is 5 pi squared over 6, I believe. And it took some high-level math to figure out that a long time ago. Not something you need to know. There you go. All right, moving on. Do you have n's in the exponent? No. Same idea as the previous one. N's not an exponent, n's not an exponent. This is not even a thing. It's not even a thing that would, how can I word this? This one's not even going to converge. I'm looking ahead at some other lessons later on. But this one doesn't have n's in the exponent. And if you listed them out, you would have stuff that really approaches 1. Like the bigger the n value, the more you're going to get like 100 over 105. Well, that's pretty much like 1. So it's going to almost be like 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, right? Not exactly, but it's going to get close to that. So not geometric, obviously. And if you care about convergence, that one's going to be a no. All right, last one in this little section and in this little video. We would like to decide what the common ratio is if it's geometric. Is it geometric? I don't know. Well, look at the signs first of all. Positive, negative, positive, negative. So if it's geometric, we're multiplying by a -1, and that's going to make our signs alternate, and that idea is going to be really important later. So let's keep moving with this idea, and let's try the tricks we've been doing. And I'm going to use a calculator because I want to, just for the sake of simplicity. If I divided -10/3 by 5, I'd get that. That's -2/3, right? -2/3. Perhaps if I do this divided by that, I'd get the same thing. And this one is totally, we're in calculus, right? This is totally doable by hand, but I just wanted to very quickly expedite the process and show you that when you do each term divided by the previous term, you consistently get that. Just there. That made the process faster. Yes, it is geometric. Yes, we are multiplying by negative 0.6 repeating. That's negative 2/3. So r is negative 2/3. That means this one is geometric. Because negative 2/3, and watch this closely now, because negative 2/3 is less than 1, of course it is, it's negative, but also greater than negative 1. It's between those two. This is going to converge. Alternates and converges. That's going to be a huge issue later as we move forward. All right, converge to what? I don't know. Time for a purple pen. Our first term is 5. First term, why do you need your first term? Boop, first term. All right, 5 minus 2/3. Right? Wrong. Watch your signs, be careful. 5 over 1 minus negative 2/3. So 5 over 1 and 2/3, which would be 5/3, which is, we'll keep going without a calculator at this point, 5 times 3/5, which is just 3.